So we want to understand damping, which is the phenomenon where a oscillating system sort of runs down. It runs out of energy. And so how do we do that? Well, the simplest case, just consider the simplest case of a mass on a spring with the drag force. So we've got returning to this basic setup, we got the origin, the equilibrium point of the spring, and let's say it's stretched past that. Okay, if it's moving, let's say if it's moving to the right, then could be moving to the left, could be moving to the right, whatever. In addition to the spring force, now there is a non-zero drag force that we have to include. So two forces work together against the motion of the object. And we, in the beginning of this chapter, we analyze it with only the spring force. But now let's sum the forces. We get ma, mass times acceleration, equals the spring force plus the drag force. Now, we have to have a specific formula for the drag force, and that is equal to, well, the spring force is minus kx, and we're going to use a linear drag force. That's what the book suggests, and I completely agree, because without a linear drag force, then it's a bit too complicated. Linear drag force, of course, means that the force doubles as the velocity doubles. It's not like quadratic drag force where the force has to quadruple or something for very fast moving, very light balloons or something. So that's the formula. And so understanding the motion is pretty confusing because in Newton's second law, we have acceleration. We express the acceleration in terms of the position and the velocity. And so algebraically, there's next to no way you're going to be able to solve this. But what you can do is express acceleration and velocity in terms of the derivatives of position. And conventionally, we also set this equal to 0. So what I'm going to do is I'm going to rewrite this as m times the second derivative of position, d squared x dt squared, plus b times the velocity, which is dx dt, plus kx equals 0. And so this is the equation that governs a system that's oscillating, but that is running down, that is approaching rest, slowly approaching rest. And so sure enough, we have this equation. Now, how do you solve it? The answer is that this is a technique that is not in your Physics 1 textbook. Folks that are engineering majors will have to see it eventually when they take differential equations. And so what I would consider you to think about is that x of t, the solution to this equation, is actually, I'm going to write it in a weird way. I'm going to write it as e to the box times t, where the box satisfies, if we think of the derivative as the, if we think the derivative as the box, then we have m times box squared plus b box plus k, no box, equals 0. And so what is the solution? So this is, again, the kind of advanced topic of differential equations. The box of this equation, the solution to this is just with the basic quadratic formula. So we can take this and say that the square or the box equals ABC, right? So let's remember our quadratic formula. The m is like the A, B is like the B, and then C is like the K. Okay, so it'd be negative B plus or minus, right? The discriminant is inside the square root, so it's minus B squared minus 4A, which in this case is mass, C, which in this case is K, all divided by 2A, so 2 times M. And so, yeah, the fascinating result that we're in no way to justify is that the solution to the position versus time graph for this thing, x of t, is, well, in addition to the starting amplitude, it'd be the initial amplitude times this exponential. Let's see if I have enough room to write it. Yeah, I have to write it big. So e to the negative b over 2m plus or minus. And I'm going to put the 2m inside the radical for reasons that'll become clear in a minute, plus square root of, well, 2m equals square root of 4m squared. And so this will be in the radical, it'll be b squared over 4m squared minus 4mk divided by 4m squared. All this times t. That's the big constant out in front of the exponential. You can go ahead and if you're willing, you can work this out. Because if you take the derivatives, if you take two derivatives and one derivative of this function with respect to t, yeah, that's what you'll get. But we can continue this, and there's a couple other subtle remarks here. First of all, when you take the exponential of a sum, you can, of course, multiply. You can factor in the exponential in a way, so you get a times e to the negative bt over 2m times e to the plus or minus square root of that thing, which I'm actually going to pull out a negative sign for reasons that'll become clear in a minute. If I pull out a negative sign, then it turns into this. It's like minus, well, if I pull this minus sign, it's like square root of minus 1 times square root of k over m minus b squared over 4m squared. Square root of minus 1 is I. And the pluses and the minuses aren't that big of a deal. So I can, from the equation, I can pretty much just drop them and get, I'm going to drop them real quick. I'm just going to quickly erase them. So I get e to the, an imaginary e raised to the I times the square root of k over m minus b squared over 4m squared times t. And so you can follow that. One of the tricks, though, is, again, this is something that you'll probably learn eventually. Maybe you've seen the equation e to the I pi equals minus 1. This lovely equation that relates all these seemingly fundamental numbers in mathematics. It's a special case of a more general formula of e to the I theta equals cosine of theta plus I sine theta. That's the general formula. And it's called Euler's formula. If this is the first time you're seeing it, then great. You'll probably see it many more times in your math and science career. But that means that I can turn this equation that I have right here, I turn that second exponential into a cosine. So I get e to the minus bt over 2m, technically times cosine of that thing plus sine of that, I times sine. But once again, we're only concerned about the real part. And so I can drop the imaginary, and this ends up being cosine of that square root times t. I'm going to call that square root omega, where omega is the new oscillating frequency of the system, equal to square root of k over m minus b squared over 2m. And so that, let me box it. This is the solution to the equation of motion for a damped mass on a spring. It's actually in agreement with the textbook. And what does that look like, actually? So we did the derivation. It looks like an exponentially decreasing cosine, if you can visualize that. I'm going to pull up an example of it and have you look at it on the PowerPoint slides. Real quick, bear with me for just a minute. Okay, so switching screens. Going on the full screen here. They talk about damping, and sure enough, they start off with this linear drag force minus B times V. They talk about shock absorbers and stuff, and they do all this setup that I just did, where you have, and they have the answer right here, okay, x of t. But the book doesn't go into the answer, or well, they also have the phase constant. Sure, the phase constant is essential as well, but the book just quotes this result, so they certainly don't derive the result like I just did. And you see the angular frequency of the damped system, and they notice in this next equation, equality next to it, they say that, well, it's technically the square root of the square of the undamped frequency minus this extra term. And so all of the damping, all of the loss in useful mechanical energy is sort of captured in this B, in this damping or drag constant, is what it's called. And you got the 4 over m squared, or the over 4m squared as well. What does that look like? It's going to oscillate more slowly. Okay, so that decreases the angular frequency and increases the period. Does that make sense physically? If you think about it, if there's constantly a drag force that the moving oscillator is up against, then it's going to take longer because the acceleration is slightly smaller, because at every point, because it's always fighting against the air in that location. So it oscillates more slowly and its amplitude decreases. So this is the figure that we see for the position as a function of time, and this is assuming that we start at the very top at A, so this would be a one with the phase constant of 0. So that's damping. And if you go back to this equation, you can repeat the same thing for a mass on a string to show how a mass on a string gets run down. Instead of omega squared, it's just G over L. Or instead of K over M for spring constant and mass, it's just G over L for free fall and length of the string. But this B squared over 4M squared term is still in the angular frequency term, okay? So that's really interesting. And sure enough, we see that the, different drag constants for different examples will, if the drag constant 0, the amplitude will just be constant, and that would be no energy loss. Energy is conserved. But bigger drag constants will obviously lower the amplitude and it'll more quickly get to 0. Energy also is decaying exponentially because of the fact that energy is proportional to half, for mass on a spring, it's half K times the amplitude squared. And so even energy itself is decreasing at the same exponential rate. So that's damping. It's a very interesting topic, and it's the case where you include loss due to air resistance, usually air resistance with a linear drag force.